I will introduce a conditional probability method to handle competing risks in a Markov model. This presentation is based on our publication titled Simplified Methods for Modeling Dependent Parameters in Health Economic Evaluations, the tutorial. The Excel, SARS and R code for the examples can be found in the appendices of this article. I thank my co-authors. In a Markov model, the probability of transitioning from one state to another is called transition probability. A conditional probability method is proposed for handling two or more state transitions in a single cycle in a Markov model along with two examples. Based on a clinical trial for patients with acute ischemic stroke, we developed a Markov model with three health states: functional dependence, functional independence, and death. Given the severity of the disease, we assume that all patients were functionally dependent at time zero. In the endovascular thrombectomy group in this trial, 44.6% patients were functionally independent, 41.3% patients were functionally dependent, and 14.1% patients had died at 90 days. When using the unadjusted method with equations 10 and 11 for the Markov model, we found that the model outputs were not consistent with the observed data. The unadjusted method is an inappropriate approach because of the multiple transitions that occur during a single Markov cycle. Previous researchers have noted this problem and proposed some methods to address it, such as proposing equations for competing events, estimating each transition rate for competing events using Kolmogorov's forward equations for transition rates, or performing eigendecomposition. But it is not always easy to implement these complex methods in practice. Here, we introduce a new approach, the conditional probability method, to estimate transition probabilities for multiple transitions in a single Markov cycle. This method can be used in both one-way and two-way transitions Markov models, examples 6 and 7, below. We provided the proofs of conditional probability given changing health states in a Markov model. We assume that all patients are at health state A0 at time 0, and all health states are mutually exclusive. Let us also assume that no patient-level data are available, and we know only the total number of patients at each health state at time t. We can calculate the sum of the probability to change health states at time t using equation 12. We can convert p sum into the transition probability of any change of health state at a desired Markov cycle length, pm sum. We can then express the transition probability of event I at the defined cycle length from the conditional probability method in a general form, equation 13. Let us divide time t into k Markov cycles. Running Markov model for k cycles and using the transition probabilities from equation 13 would result in the same probability of being at health state I at time t from the observed data. Example 6 for stroke patients illustrated of applying the conditional probability method in a one-way transitions Markov model. This method consists of 4 steps. Step 1. Estimate the total probability of transitions from a functional dependent state, all patients at this state at time 0, to other health states at 90 days. For mutually exclusive events, the probability of either event occurring is the sum of the probabilities of each occurring. In this case, the probability of changing health state over 90 days, p sum, moving to functional independence or death, was equal to 0.587, 41 plus 13, divided by 92. Step 2. Use equation 10 and 11 to calculate the event rate and monthly probability of changing health state. The rate of changing health state was 3.54 per patient year, and the monthly transition probability was 0.255. Step 3. Calculate the conditional probability of functional independence and death, given the changing health state. The conditional probability of functional independence was 0.759 equals 41 divided by 41 plus 13, and the conditional probability of death was 0.241 equals 13 divided by 41 plus 13. Step 4. Calculate the monthly transition probability for Markov model. The monthly transition probability to functional independence was 0.255 times 0.759 equals 0.194, and the monthly transition probability to functional independence was 0.255 times 0.241 equals 0.061. We ran our Markov model using the monthly transition probabilities by the conditional probability method. The probabilities of stroke patients in functional dependence, functional independence, and death states from the Markov model at 3 months were same as those reported in the clinical trial. We also examined this method in a Markov model with 4 health states using the same example. We did not change the functional dependence and death states, but we did define no symptoms, MRS score 0, and minor symptoms, MRS scores 1 to 2. We ran the 4 health state model using the conditional probability method, and our results were consistent with the observed data. The conditional probability method was applied to more complex scenarios in example 7. Allowing for two-way transitions from health to disease, and from disease to health, and for patients to be allocated to different health states at the beginning of Markov model. We assumed that a cohort of patients with stroke were assessed by physicians at 6 and 12 months post-stroke. Doctors categorized their health states in 4 health states at both visits: no symptoms, minor symptoms, functional dependence, and death. However, no information was available about patients' health states between 6 and 12 months post-stroke. As a result, we made the following assumptions related to transitions. 1. If a patient was in the same health state at both visits, we assumed that they did not change health state during the period between 6 and 12 months. And 2. If a patient was in different health states at the 2 visits, we assumed that they experienced just a single transition in this time period. Partially using the data from the Oxford Vascular Study for stroke and with some assumptions, we developed accounts of transitions matrix for a hypothetical cohort. The row total was the number of patients in each health state at 6 months post-stroke, and the column total was the number of patients in each health state at 12 months post-stroke. For example, of the 208 patients in the functional dependence state at 6 months, 144 patients remained in that health state, 5 transferred to no symptoms, 35 transferred to minor symptoms, and 24 died between 6 and 12 months post-stroke. Let us assume that transition rates are constant over 6 months, from 6 months to 12 months, for all transitions, and use monthly cycles for 6 cycles of the Markov model. We used the methods introduced above to estimate the total transition probabilities and conditional probabilities for patients at 3 surviving states, tables A13, A14, and A15. We ran the Markov model for 6 cycles and got the same results as those, column total, in table 4. We have illustrated the calculation process in Microsoft Excel. It should be noted that we needed to define the new states. No symptoms, minor symptoms, and functional dependence, for patients who were transferred from other health states, given that these patients were not allowed to transfer to other health states under our assumption of up to 1 transition between 6 and 12 months. Thank you.